Hey everyone, today we'll be focusing on binary search tree today, particularly focusing on a brief overview for our full binary search tree. And without any further hesitation, let's get started. And now we're going to be going over a brief overview of our full binary search tree. So to be able to give an overview, so we developed our header file that we have already made, where we have a public structure of a node, where we also consider the left and rightmost nodes in our binary search tree for a full tree overall. We have a function to be able to print the tree that we've already set up in place. And then we also have a private instance as well to initialize our height, and have another function to print the tree depending on the level of height, and then also outputting the direction of the number of nodes on both the left and right most of our subtree. So this is the helper function that we use. And then we use the helper function inside of our main function that we call inside of our main C++ class. Now, to give an overview of a full binary search tree, a full binary search tree is a type of binary search tree in which every other node has, other than leaves, has exactly 2 children. So we notice in particular our nodes over here, and they have 2 children. We notice here and here overall, and since these are leaves, since they are the very end of our tree, they technically do not have any more nodes at their ends as well. We notice 1 is the root. It has exactly 2 children, 2 and 3. We have 2 over here, and does it have 2 children? Yes, it does. It has 4 and 5. Then we have 3, which has 2 children, 6 and 7. And then the nodes 4, 5, 6, and 7 are leaves, and they do not have any other children. Therefore, it is considered a full binary search tree. And then we have imported our libraries as well, iOS Stream, depending on our IDE, our queue and stack for breadth for search, and then depth for search, and we include our header file as well. We have a public instance for a binary search tree where we've initialized our root node that we will call upon inside of our main class. We have already done our inserts, insert requirement for our node for a binary search tree, and we determine where to insert on both the left and the right side as well. And we always have a base case of where if we do not see the node, then we have to return the data of the following node. So this is just what we have for our base case. And we have just going over edge cases in general. And we remove a following node by checking both the left and the right side. And then we do a swap technique by using our temp to be able to delete the node and then replace it with our following temporary node as well. We do it for both the right and the left side as well. It's interchangeable as well. It's just the order of what we did it. Now, we also need to consider we have to consider other edge cases as well, which is what if whenever we remove a following full binary search tree that the node has 2 children. Well, that means we need to have a helper function that we created called min_value_node. And min_value_node is going to do the same thing that we did before, except we're going to have a node called current, and we need to check on either the left or right side. So we already took care of this by having a swap technique for the right side. Now we are going to be doing it for our left side as well overall. And we just have this node right over here as our parameter, and we can just put the node that is on the right side as well inside, and then it would actually follow the logic at the same time. So I'll just take care of that. And also, mind you, since we're also focusing on the leftmost to the rightmost, that is why overall that we have removed our following node from our full binary search tree as well. We did a number of traversals. We did in order, pre-order, and post-order traversal, where once we have gone through it, we have done in order, where I'm just going to move this up over here. In order traversal, it goes from 3, 5, and 7, then 10, 15, 20, all the way to 25. Notice in particular that we have done 3, 5, and 7, and then we go all the way up to 10, then we do 15, 20, and 25. Now, pre-order traversal, on the other hand, goes 10, 5, right over here, 10, 5, 3, 7, then 20, 15, 25. We notice over here goes all the way down here, then 20, 15, 25, leftmost to the rightmost. Then finally for pre-order, then finally for post-order, we go from 3, 7, and 5 to 15, 25, and 20, all the way up to 10. So we're focusing on the subtrees overall to get to our root, hence post-order, post ahead as well. Pre-order is focusing on the root, goes to leftmost. all the way to the rightmost. And then we have done in order. We focus on the leftmost subtree, and then we go up to the root, and then we do the rightmost subtree starting from the left as well. Then we did breadth first search iteratively, where we have our queue that we have initialized, and we already put a node inside of our queue to be able to check, and then we push our following queues, data points on the leftmost to the rightmost. It's already over here, 10, 5, 20, 3, 7, 15, and 25, and breadth first search goes based on level, so we notice these circles over here go from the leftmost to the rightmost. Then recursively, we also done the same thing where a function is being called inside of a function. Then we did depth first search iteratively, where depth first search focuses on stacks, unlike breadth first search, they focus on queues, as usual. And depth first search, we did the same type of pattern design we did for breadth first search over here, except for the differences is that we've done depth first search with a stack where we push the following node, and then we output our following data, and we check the rightmost to leftmost as well. Then we also perform depth first search recursively as well, got the same output, and notice how we get from the leftmost here all the way to the rightmost, 20, 15, and 25, as we have done so already. Then we also did the theme of helper functions as well. So these were the main functions that did all of the work, and they're helper functions in this case because they're not the functions that we are calling upon when we are inside of our main function as well in C++. Instead, these are our functions that we have made that are going to be called upon and calling upon the other functions that we have made all the way at the top. Accordingly over here. We've done insert, remove, in order, pre-order, post-order, breadth first search iteratively, breadth first search recursively, depth first search iteratively, and depth first search recursively. Sorry about that. Then this is our main function. We input the following tree as well, and we used ASC IIrt as well to be able to output the following tree. And we insert the following nodes inside. We print out the tree. Then we do in order traversal, pre-order, and post-order. And we do the necessary, after we've done the traversals, we then do breadth first search and depth first search iteratively and recursively as well. And we also remove the following tree and then output our following tree as well after we have removed our following node. And so yes, this was a brief overview for creating a full binary search tree. Now that we have already done so, now let's head over and then practice on not only the C++ syntax for us to get fully accustomed, but to be able to build out our other binary search trees as well. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.